Welcome everybody. My name is Martin Knoche. I'm from the chair of Human-Machine Communication at the Technical University of Munich. In this talk, I'm going to present my paper, the Explainable Model-Agnostic Similarity and Confidence in Face Verification. So in our paper, we propose a novel strategy for explainable face verification. That means we generate model-agnostic explanation maps and a confidence score. And moreover, we developed a web platform to not only present our results, but also provide a platform to browse through different data sets. We use the LFW dataset and its derivative, like the cross-age, the cross-pose, the similar looking, and the cross-quality LFW dataset. And this platform should also help to browse around to the specific image pairs and see what are the model prediction for that pair and what is the explanation looking. So get a deeper understanding in what pairs might be classified, misclassified, or classified correct. And we think that this approach might not be limited to face recognition and can be potentially applied to other binary decisions. And in the future, we would like to investigate on, maybe is it possible to assist a machine? Like we would like to find out which pairs are misclassified, and maybe humans can help on these pairs to classify them correctly, and how the explanation maps can help them or might not help them. So that's what we like to see, or what we like to study in the future. So then a brief introduction to my to the agenda of my talk now. So I first introduce the topic, then I will explain the methods, how we calculate our confidence score and how we generate the explanation maps. And after that, I'll show you some experimental results and we'll briefly go through our sensitivity studies. At the end, I draw a conclusion, finally give an outlook of our future works. And if there's enough time left, I will show you a demo of the web platform and show you what it looks like. So machine learning has shown impressive performance in tasks such as image and natural language processing, particularly with the development of deep learning. And it has influenced many fields, including medicine and security, where high accountability is important. And these systems are often considered as black boxes because their internal workings are not known. And explainable artificial intelligence emerged to address the need to understand these models. And they offer benefits to users and developers, and its explanations should be interpretable and accurate. And there are model-agnostic tools, for example, like the LIME and model-specific approaches, such as the well-known graded weighted class activation mapping methods. And in this work, we focus on a model-agnostic approach for face verification and provide explanations through some kind of similarity maps. And instead of using the common used cosine distance to determine the certainty of a decision, we calculate a more natural and maybe more understandable confidence score to see how confident is the model in its prediction for a pair of image. And so how do we calculate our confidence score? So yes, you can see here, it's a histogram of cosine distances for pairs of, I think it was the LFW dataset. And you can see in cyan shows the counts of the genuine pairs for the given distances, and red are the counts for the imposter pairs. And because the model is not 100% correct in predicting, both distributions are overlapping near the decision boundary, which is about like 0.7, I think. And we think that one can interpret the distances for non-overlapping areas as 100% confident. And right at the decision boundary, we consider the confidence as 50%. So the model is 50%. It's just guessing if the distance is just at the decision border, and if the distance is far away, then we consider the model is pretty confident. And as this is most of the time, it's not a symmetric distribution because the decision boundary is somewhere not in the middle. So that's also a reason why we establish this score, to have a more understandable score. And the idea is now to build the binwise ratio of those two distributions. And you can see the points lying on this curve. And after that, we finally fit a sigmoid curve on these ratio points to get a smooth distribution between 0 and 1. And then we flip the curve for values above the decision boundary to get the aforementioned confidence values from 50 to 100% for all predictions. And how do we generate our explanation maps? So the core principle of our model-agnostic explanation approach is to occlude parts of the image or parts of the face and measure the deviation of cosine distance for that image pair. So if the feature distance between two images is decreasing, we interpret the occluded area as dissimilar, and vice versa, similar for a greater distance. And with the systematic image occluding, like we occlude systematically each part of the image, we can then measure the influence on the cosine distance of every part of the image, and hence visualize it in a two-dimensional map. And we propose 3 different methods. So starting with the first one, there we have the first, or one of the images has an occlusion at a fixed location, and then we take the average of the distance deviation to the other image with occlusions at any different locations on that image. And then we have another method. So like method 2, we have one image which has no occlusion, and the other image has occlusions at any particular location, and we measure that deviation and generate the map of it. And the third method is that we have occlusions on both images, but at the same location. So we just move the occlusions on both images, go systematically through the image, and then build calculate the deviation of the distance and build the map. So in the first 2 methods, we have different maps for each of the image of the pair. So you could have the first image of the pair has like similar areas, and the second image of the pair has at the similar areas at different locations, which is probably not that naturally to interpret, but we will see it later. And that's why we also added the third method, which has explanation maps which are equally for both images of the image pair. And we then, after we build those maps, we use a simple color blending algorithm which blends the input image with our generated explanation map, so you can see the explanation directly on the face. And to do that, we first transform the image from the RGB channels to hue, saturation, and luminance channels, and then use the luminance channel from the input image and hue and saturation from the explanation map. And then we transform that back to the RGB color space, and that is our final explanation. So here you can see some examples of explanation maps for 3 genuine and 3 imposter pairs. And in green highlights the similar areas, and red highlights the dissimilar areas. And the faces for the genuine pairs are mostly colored in green, so that means they have highly similar areas. And as you just to note, we used the third method for this, so that's why both explanation maps are similar for both images. And for example, if you look at the imposter pairs, there's always the forehead considered as similar, which is probably naturally because it might not have that much information for the identity, but eyes and nose and mouth are considered as dissimilar, which we think is somehow understandable why this is considered as dissimilar. And here you can see an idea what the difference of these 3 methods looks like in terms of the results. So we have generated maps for 2 imposter pairs and 1 genuine pair in the middle. And method 1 and 2 are principally generating the same explanation, so there's not a big difference, we would say. But method 3 is generating other explanation maps, so that's looks a little bit more different. And this allows probably a more natural interpretation of similar areas. And in other words, we can say that the nose and or the mouth is considered similar because it's at the same location on both images. And in this method is not able to highlight similarity between, for example, left eye of the image 1 and left and right eye of the image 2. So I don't know if you really get this, but if you have, for example, if you have 2 images and one has one side occluded and the other one has the other side occluded, then we cannot get really good explanation maps from our third method because it just compares the same locations at both images. But for that case, probably method 1 or 2 is probably more suitable. But in general, if there's the complete face visible, it might be better to have, to use the method 3. But it depends on the application, we think. And here we just experimented with the manipulation of images. So parts of the image 1 are just copy pasted into the image 2. And the result shows that our algorithm correctly classifies the more similar areas, and the rest of the face is more dissimilar. And we conducted some sensitivity studies to see the influence of the shape, coloring, edge, quality, and size of our occluding patches used in the systematic occlusion. And using the third method, the resulting map for both images is shown on the top right. And while size and edge quality seems to have the most impact, the color or the shape of the patch doesn't seem or seems to have less impact on the resulting maps. So in conclusion, this work conducts further research on explainable face verification and proposes a novel strategy to generate 3 different explanation maps and calculates a confidence score for a face verification model's predictions. And with our explainable face verification platform, that's the web platform, we contribute a tool to further investigate the behavior of some state-of-the-art face recognition networks and demonstrate the interpretability and accuracy of our approach. And however, our proposed algorithm can only highlight highly locally appealing similarities, and our method is not able to reveal the global similarities. So for example, like the skin color or the shape of the face isn't detected by our algorithm. And we focus in this work explicitly on faces, but we think that's probably not limited to faces and can potentially apply to other binary decision problems. And in the future, we plan to investigate a joint application of machine face verification and humans. That means we would like to see if image pairs in which the machine is less confident can be better classified by humans. And we also would like to study the benefit of those explanations for human decisions. In other words, which explanation map actually helps humans in their decision for a face verification. So I think I have just maybe 2 minutes time to see or to look at the web platform, how it looks like. I hope we have here a good internet connection. So this is our platform, and we have this first introduction page. And what is the core principle of this web platform is this viewer section where you have you can browse around through the different data sets, and you can select which model. We just added 2 models right now. We plan to add more of the state-of-the-art models to browse around for them and see the explanations for them. And we also provide like an overlay mode. You can see just the explanation maps. You can see only the image. You have our 3 different methods here. And right now I'm at the mobile version, but normally you have some errors and just can click through the image pairs. And here I have to put it manually, but yeah, as you get an idea, I think. And the other section is the Explorer section. This is basically a table containing all the image pairs of the data sets. And for example, we have the similar looking LFW dataset. And here we also included 2 models, for example. And here you can, for example, filter for a wrong prediction. And then you can sort the table for the confidence if it's working. Yeah. And you can see also some additional information about what was the distance calculated and what's the threshold for the decision and what's our post confidence for that. And yeah, here I think you probably get a feeling about which pairs are not classified and compare different methods here. And yeah, so I think that's it for my presentation. And yeah, I'm happy to answer any questions if you have. Thank you very much.